Okay guys, these are the notes on independent versus dependent quantities. This is our stop 1, pit stop A notes. Okay, so you should have glued these in your journal already. Alright, so starting. Independent and dependent. So independent and dependent quantities. In math, the input value is also known as the independent quantity. The way I remember this is input and independent both start with I. Okay, so they both start with I. So the input value is also known as the independent quantity. The value of the output is known as the dependent quantity. So we have two options, independent or dependent. Remember, input and independent both start with I, so the input is the independent and the output is the dependent. Okay, this last little vocab is variable. So variables or symbols, usually letters, are used to represent unknown numbers. So for instance, if there's some equation and I don't know a number yet, I'm going to use a variable, usually a letter, okay? It's usually the letter X, just so you know. Usually the letter X. Alright, so a variable is a letter that represents a number that I don't know yet. Okay, for instance, like X plus 3, that's saying some number plus 3. So X is a number I don't know yet, and I would be adding 3 to it. So we use this variable, X, to represent a number that we don't know. Alright, so let's go down here and look at input-output tables. Well, first off, let's figure out what's the independent and dependent quantities. Remember, independent and input both start with I. So input is the independent. Output is the dependent. Remember, input and independent both start with I. Input is always the X. Output is always the Y. Always, always, always. Okay, so input is X. Output is Y. So for instance, here is our rule, X plus 7. All right, that's saying some number plus 7. X is our variable. Some number plus 7. Well, our input over here, what this is telling us is just saying, oh, okay, well, if X is the input, here's a number 10. We're going to replace that with the letter X in our rule. So this is saying if X equals 10, well, if X equals 10, I would replace 10 where the X is plus 7. Well, what is 10 plus 7? 17. Think of our input-output machines that we made. Whatever we put into the rule and our output depends on what we put in. Okay? This 17 depends on me putting a 10 in there. If I put a 9 where the X went, I would not get a 17. So the output, the number you get here, depends on what your input is. So let's try it with this one. They tell us they want us to replace X with 5. So here's our rule. Instead of X plus 7, I'm going to make it 5 plus 7. And 5 plus 7 is 12. Same thing. They're saying X is 3. So let's replace 3 with X. 3 plus 7, well, that would be 10. Okay, so we just created an input-output table. All you're doing is telling, whatever it's telling you the input is, or the X, you're taking that number and you're substituting it in for X in the rule and then solving, basically. So let's look at B. Same thing. I'm going to replace 10 with X. So 10 minus 2, well, that gets me 8. What about this one? Replace 12 with X. 12 minus 2, well, 12 minus 2 is 10. 14, I'm going to replace with X, so instead of X minus 2, it's going to be 14 minus 2, and that is 12. So I just created that table. Let's look at letter C. I wonder how we read this. Well, there's not an addition or subtraction sign in there. That's just 5 right next to an X. Well, if you remember, a number right next to parentheses means to multiply. So this is like saying 5 times X. So when I input my 2 in for X, that's the same as saying 5 times 2, which is 10. Again, I'm going to replace 4 with X, and 5 times 4 is 20. Same thing, I'm going to replace 7, okay, and 5 times 7 is 35. There we go. Now on this one's a little different. It gives me the outputs, and I need to find the inputs. I can still use the rule, but in order to get the input, I'm going to work backwards. Work backwards. All right? So this is telling me some number minus 4 is 8. Some number minus 4 is 8. We'll have to figure out what that number is. So to do that, I'm going to work backwards. All right, so instead of subtracting 4, what's 8 plus 4? Well, 8 plus 4 is 12. So we're going to say our input is 12. Let's plug 12 in for X just to make sure I did it right. 12 minus 4, does that equal 8? It sure does, so we did it right. Same thing, let's work backwards. Instead of subtracting 4, let's add 4 to 10. Well, 10 plus 4 is 14. And now let's plug our 14 back in just to make sure. 14 minus 4 is 10, so yes, I did that right. Same thing, instead of subtracting 4, I'm going to add 4 to 6. I'm working backwards. When you work backwards, you do the opposite. Okay, so 6 plus 4 is 10. If I plug 10 in for X, just like we've been doing, 10 minus 4 is 6, so check, I did that right. So it is possible for us to give you outputs and you work backwards to get an input. If I had given you these outputs right here and asked you to work backwards instead of multiplying by 5, what would you have been doing? Well, the opposite of multiplying is dividing. So 10 divided by 5 is 2. 20 divided by 5 is 4. 35 divided by 5 is 7. Again, once you get your answers over here, make sure you plug them back in to make sure you got the right thing. Okay? Last part. These values can also be represented on a graph as ordered pairs. So not only can I take a table like this, an input-output table, but I can also represent it on a graph as ordered pairs. So for instance, Jamie has 2 game tickets more than 3 times her brother's game tickets. The rule, 3 times X plus 2, remember a number next to a variable means to multiply, so 3 times X plus 2, where X is her brother's tickets, can be used to find Jamie's number of tickets. So here's her brother's tickets. We're going to plug our X values, our input or independent values, and for X into our rule to get our output or Y's or dependent values. Okay, so 3 times X plus 2, and they're telling us they want us to replace X with 30. So 3 times 30 plus 2. Well, 3 times 30 is 90, and 90 plus 2 is 92. Now I could write my coordinate pair or ordered pair. Remember, ordered pairs are X, comma, Y. Well, these are our X values. It tells us right there. So 30 is my X value, and these are my Y values. And so when I plugged in 30 for X, what did I get for Y? Well, I got 92. Okay, so let's finish our table, and then we'll come over here with our coordinate pairs and we'll graph those. So again, I'm going to plug 40 in for X. So 3 times 40 plus 2. Remember, with PEMDAS, you have to multiply before you add. So 3 times 40 is 120, and 120 plus 2 is 122. Now, if I was going to write my ordered pair, it'd be x, comma, y. So 40, 122. Last one, we're going to plug 50 in for x. So 3 times 50 plus 2. 3 times 50 is 150, and then plus 2 is 152. Write my ordered pair, 50, comma, 152. Now I can go over to my graph and graph my ordered pair. So remember, you always go across before you go up. If this is my x value, 30, remember 30 is x. Well, here's my x-axis, so I'm going to go over to 30 on the x-axis and then up to 92. And I know that we don't have a number over here, so we're going to try and get it as close as we possibly can. The next one, 40, 122, so over to 40, up to 122. And then 50, 152, so over to 50, up to 152. Again, just get as close as you can. It doesn't have to be perfect. We always start from 0, and we're going to connect our dots. And we want to make sure that this makes a straight line, because if it doesn't make a straight line, we did something wrong. A straight line, this is called a linear relationship. It's not a linear equation yet because we don't have an equal sign. So we'll call it a linear relationship. And look at what word is in linear. Line. So that means a linear relationship needs to make a straight line. If you had a dot way up here and it made a big zigzag, you would know that you did something wrong. So that's a way to check yourself, so you can go back and make sure that you plugged in and did your math right over here. So this is independent and dependent value notes for stop 1, pit stop A.